A very good morning, everyone. I hope you're doing great on the other side of the screen. Thank you for joining in on today's topic about uncovering Azure's silent threats, a journey into cloud vulnerabilities. So, little about myself. My name is Nitesh, and I'm from Sikkim, a small state in India, and I'm really honored to be here at Black Hat, USA. Although virtual, but that's okay. I work at Trend Micro with a focus on cloud and container threat research, so mostly threat hunting, threat modeling, honeypots, and all that stuff. I've been in the threat research space for around 2.5 years now, and I am experienced with bug bounties, CTFs, and security operations as well. So a fun fact about me, I wrote my first song in 2018 and my first exploit in 2009. For the exploit, you need to ping me on Twitter to know what it was about. It's really funny. It's related to a game called Spider Solitaire. And the other fun fact is that this is a picture from my last trek that I went on with my friends, where I trekked for 4 kilometers with a minor ACL tear. So yeah, that's a win for me. So those are my socials. You can connect with me there. Now on to the journey. We will be exploring the iceberg in the form of 3 main chapters. An introduction of what we are going to talk about, the issues that we found during our journey, few angles of research that we tried and learned along the way, followed by the conclusion. So let's begin the journey. There has been some buzz around cloud service providers fixing vulnerabilities reported in Jupyter Notebook-based services. Be it Azure, be it AWS, be it GCP. Each have something in common, Jupyter. So is there something off or something fishy with notebooks in general? So I pack my bags and head to the Azure portal and search for services based on Jupyter. And I'm greeted by this one interesting result about running Jupyter notebooks in a workspace. And folks, I kid you not, this is where it all started. In 2019, there was a prediction in a Gartner report which talks about a 5-time increase in the usage of cloud-based AI services by 2023. And as of 2023, it kind of makes sense as companies are seeking to use AI in their products and services. They want to create ChatGPT-like chatbots, and they want to train LLMs on their own data sets. And when ChatGPT was released, like everybody else, even I was curious to know how is this environment looking? Like how does the underlying platform look? And this video clip from May this year kind of makes sense now. So what is Azure Machine Learning? Azure Machine Learning is a mammoth of a service, let me tell you. So we will go with some basic stuff to understand the vulnerabilities that we found in the service. So AML, Azure Machine Learning, is a machine learning as a service offering from Microsoft in Azure. It uses a mix of user-managed and Microsoft-managed services. In AML, you basically create a workspace, which is like a centralized place to manage all your machine learning-related activities and artifacts. You can access a workspace using your browser itself, VS Code, or the Azure ML API as well. But what do you do on a workspace? You basically work. You create your Jupyter notebooks, run experiments, create and import datasets, create training or inference environments, deploy your machine learning models as endpoints, and you do all of this just from the studio itself. Like this is possible. You could perform your entire MLOps just from the AML studio and working on the workspace. So the workspace is dependent on certain Azure services on the user's end. So when you create a workspace, the resources for these services are created except for the container registry. That is not a mandatory service or a resource to have right now. In Azure Machine Learning, the data scientists or general users would perform MLOps. And these are the various compute targets that are provided by AML. So on these compute targets, you run your Jupyter notebooks, training scripts, or you literally host your machine learning models as endpoints. So you have a cluster. Compute cluster is basically a managed cluster of virtual machines with multi-node scaling capability, and it can be GPU enabled as well. We have Kubernetes clusters, so you can attach your existing Kubernetes cluster to perform your machine learning operations on it. Or you can also attach your on-premises Kubernetes cluster as well. Attached compute, so you can attach virtual machines, Databricks, HD Insight resources to perform your training inference as well. In this talk, specifically, we'll be focusing on compute instances. So compute instances are basically managed Ubuntu virtual machines. So when we say managed, everything is managed by Microsoft, like patching of the host OS, patching of various issues if they are found, and the OS image contains various other tools that are used by developers, such as Jupyter, VS Code, Docker, Python, R, and all of these things. This is where you run your code and you perform your model training. And each workspace has a storage account which contains your machine learning related entities. To access data in a storage account, you need something that is called a data store. Data stores are basically a reference to a workspace's storage account, and they help avoiding storing your access keys or credentials in your scripts. You can simply refer to the data store to access the file share or the blob storage. And these file shares and blob containers are basically used to store your notebooks, datasets, logs, models, scripts, and everything. We can browse the storage account using a storage explorer and view the file shares and blob containers that are referenced by the default data stores that are created when you create an Azure Machine Learning workspace. The interesting bit here is data stores in Azure Machine Learning support credential-based authentication for file shares. This basically means that if you want to work with Azure file share, the username and the password combination will be used, where the username will be a storage account name, and the password will be the storage account's primary access key. So these credentials are of the storage account, and these will be used if you want to work with file shares. All right. Additionally, multiple users can create compute instances in a workspace. And by design, there cannot be two owners for one single compute instance. Also by design, any user in a workspace can access the other user's files because all of the files are stored, like the Jupyter notebooks, scripts, they are stored in the Azure file share. And this Azure file share is mounted on each compute instance in the workspace. With this background and a very simple introduction of Azure Machine Learning, we begin with the first episode, where a data scientist is actually looking for the keys. Did you see my keys? While examining the different folders and the files on the compute instance, we come across a directory structure, which looks like this. Now this directory structure is of Azure Batch. So we take a quick look into what Batch is. So using Batch, you can basically run your large-scale workloads in Azure. For example, you can use Azure Batch to process images at scale by distributing the entire workload. So these are some basic terms to understand as we proceed. Remember, it's a journey and not all pauses are beautiful, right? So we have something that is called a node. So nodes are basically your virtual machines. They are based on Linux or Windows. Pools are basically logical group of nodes. So you can group nodes together in one single pool. Jobs are collections of tasks. For example, if you are trying to run a script 10 times to figure out if the script is performing on some different level for each and every run. And each and every individual run of a job is called a task. So you can think of tasks as commands that you supply to run on Azure Batch nodes that are part of a pool. So you can also monitor and download the output logs for tasks. In Batch, you have a concept of a start task. Basically, the start task runs when a node starts up. The files, configuration, the output of the task are stored in the path in green, that is mount batch tasks under startup. And the output is stored in standard error and standard out based on the type of errors that are generated or the type of output that is generated when you run a task. As we saw previously, the file share is mounted on a compute instance. So we had a question, how is the Azure file share being mounted on the compute instance? Since it uses credential-based access So it would be interesting to examine, are the credentials being stored or logged somewhere? Turns out we were able to find the exact command that is being run on the startup under the start task, where the Azure file share is being mounted on the compute instance. So the output of the start task is logged in the standard out and the standard error files under the startup directory. And we saw the username and the password, like the storage account name and the primary access key of the storage account, being logged in clear text as is in the error logs. On top of that, this command is being run as sudo. So the same command gets logged in the authorization logs as well, which is var log auth.log. So we reported these instances to Microsoft and we waited. Few days later, we came across an instance where the password field itself of the entire command line was masked. So this was the fix. And we noticed the fix attempt after our reporting. Then we had a query to ourselves: what if there are more such instances of credentials being logged or stored in clear text? Hence, we started looking for more such occurrences on the same compute instance. So Azure Machine Learning uses certain agents to manage compute instances. So when you are talking of managing a compute instance, that means diagnosing, monitoring, and making sure that the compute instance is healthy, etc. So these agents are installed on all compute instances and they are maintained by Microsoft. So the agents are located at this working directory under the start task. So these agents need configurations, like certain configurations to perform actions. And these configurations are supplied as environment variables. And the file that is supposed to be supplying the environment variables to these agents, because these agents run as services. So the files are located in the working directory under DSI. Turns out that the configuration for two of those agents, named DSI mount agent and DSI idle stop agent, contained the storage account access key again. So this was twice. And this was found when we were trying to figure out how were the previous issues fixed. But it is interesting to note that why is the environment variable named password? It could have been something else like storage account key or something else as well. Turns out the password argument can be supplied as an environment variable named password. That's interesting. And this issue was found while trying to understand how were the previous issues fixed. Nevertheless, all the instances of storage account credentials being stored or logged in clear text were fixed after our reporting. And that brings us to chapter 2. Since credentials are being logged and stored in files, and this was acted upon and fixed, we had a thought. Are there credentials that are incoming on the compute instance? So we begin chapter 2. Wait, is that my token? A user can access a compute instance using Jupyter Notebooks, Jupyter Lab, Jupyter Terminal, and a browser embedded terminal as well. So these requests are proxied to the compute instance by a load balancer in between. So the URL will look something like this. So you have the compute instance name, followed by the region, followed by instances, azureml.ms, followed by the URI. So let's say if you want to access Jupyter Lab on a certain compute instance, that is AML, in the East Asia region, provided you have the proper set of role-based access control permissions, then you need to enter this URL. And you can go there from the AML Studio as well. So you can access the compute instance using Jupyter Lab, and this is how it looks on the browser. And this is how it looks on the browser embedded terminal. Oh yes, the default user, Azure user for a compute instance, can assume sudo privileges without needing a password. So that's a thing there that will be used later on. These browser-based terminals can be accessed by a user with the proper permissions. And the authentication flow in Azure ML looks something like this. So client requests for a token to Azure Active Directory, the ARM token, the Azure Resource Manager token. And this Resource Manager token is used to call the Azure Machine Learning service. And then an AML token is generated using which all the AML related actions are performed. So all the incoming requests to the compute instance are received by an Nginx proxy that listens on port 44224. There are certain certificates that are used, and This proxy configuration requires client-side certificates for authentication. There are some checks on the subject and the issuer CNs of the client-side certificate. Now, the proxy checks for a specific header that is XMS target port separated by hyphens if it contains a numeric value. Later, a variable that is proxy host variable that is set to the proxy pass directive for URLs that are trying to access the Jupyter-based WebSockets, basically the terminal, or any other path under the root resource. So these requests are forwarded on the basis of XMS target port. Basically, an incoming request on a compute instance shall have this header already populated. And this request will be received by Nginx, which listens on 44224. And based on the value of this port, of this header that is XMS target port, the request will be forwarded. In this case, 8888 is the default port for Jupyter, and that's the same port on which Jupyter service listens on a compute instance. And this is all fine, but the interesting bit here is the Nginx access logs that are stored in var log nginx access.log. These logs are basically enabled by default on Nginx. And these are not disabled by the compute instance. So we found this issue using a good old friend called TCP dump to view the network capture. So when a user closes a terminal and when they click on terminate to terminate the underlying process, a GET request is sent followed by a delete request which removes the terminal. But the interesting bit here is we have a token. There is a URL parameter named token which contains the JWT of the compute owner, like the compute instance owner. So we used, basically we just decoded the AML token and we see the audience for this, and okay, so we have a token. But why was the token even there in the URL parameter? So turns out, while we were exploring the documentation for Jupyter server, we see that the token can be provided in 3 different ways. It can be provided in the authorization header. The other is you can specify it in the URL parameter, that is named token in this case, or as a password field on the login form. And since Nginx logs access attempts at a default path, the token was logged. We reported this issue to Microsoft and they promptly fixed it as well. After all, these are just credentials stored or logged in files on compute instances. What could go wrong and what is so risky about it? So developers have been observed to share error and debug logs from their systems on public platforms like GitHub. If they are not quite aware of the fact that these logs may at times contain credentials, that too in clear text, that's a silent risk that they are being exposed to. In this example, we see the request for the batch error logs, which in our case contain the storage account access key, that too in clear text. There have been various dependency confusion attacks with NPM and PyPy, and this one is specific to a machine learning library that is called PyTorch, where the attacker-controlled code was exfiltrating credentials after gathering them from files. So as you can see, the first 1,000 files in the user's home directory were exfiltrated. So with the storage account access key being logged and stored in error logs or just files, it just adds to the risk. If an attacker is able to compromise a file share, then they can trivially compromise the entire storage account, which in turn basically means the entire workspace. Let me show you how. Consider a scenario which might be likely to happen. We have a workspace with 3 users, each having 1 compute instance. Each workspace user's files are stored in the same Azure file share. If an attacker can get hold of a user, which is anyway a high degree of compromise, or a compute instance which has these credentials being stored and logged in clear text, or the file share where you have your Jupyter notebooks, scripts which are run on compute instances and compute targets and clusters, the entire workspace could be compromised. Now picture this with a scenario where users could actually view each other's JWT token. Suddenly, the bug becomes massive. According to the documentation for data stores provide a way to secure the connection information, such as storage account access keys and SAS scripts. Using them, you don't need to store these credentials in your scripts, and this is a very cool feature. However, if the storage account key itself is getting logged in error logs, auth logs, or the environment variable files, that kind of creates a difference. And remember, the default user, Azure user, can easily assume the sudo permissions. So that's not even a boundary here. So we reported this set of issues, like these set of issues, to Microsoft. And now the same issue of credential logging might have been lurking in your environment as a silent threat. These issues were fixed by CVE 2023-23382. And now the JWT is not even observed to reach the compute instance. And the storage account access key is not logged or stored in any of the files on the compute instance. Some takeaways: be it logging or storage, credentials in clear text, they are unhealthy and risky. And it's very crucial to close loopholes and lower the risk in case of a compromise, especially when we have observed in the past that cloud-focused threat actors just love credentials from files. From the design of such environments, you also need to be aware of the associated risks. While using open source tools, you need to review the configurations, like review them before you use them. Forwarding the supplied JWT of the user to the compute instance was still okay, but logging the token? Definitely not. Additionally, URL parameters shouldn't contain sensitive information, as we never know that there may be inline proxies or different components that they pass through and where they are ending up anyway. This is something that was shared by Daniel Meisler in the blog. Additionally, developers need to be aware of possible security implications that may emanate while sharing error logs on public platforms. The issue of credential leakage can turn out to be critical, especially when the users are not even aware of them. Now with that, we embark on the third and the almost final chapter of Spying the Scientist. In Azure Machine Learning, one can create compute instances in VNets, and you can specify the VNet plus the subnet during the creation of the compute instance. This can be an observed scenario where the training environment needs to access other Azure services via private networks and not over the internet. And using VNets is something that Microsoft recommends as well. A simple environment would look like this. There's a virtual machine that lies in the user's own subscription. Remember that the compute instance is a managed compute, and it lies in the Microsoft subscription. So we have a scenario. Let's say the Azure virtual machine on the user's end gets compromised. What could someone from the Azure virtual machine do on the compute instance? Are there any ports open on the compute instance? Let's find out. So we fired up our favorite tool Nmap and checked for open ports. We come across a port which is 46802. Remember, we have the compute instance's access, so we figure out that there is a process named DSI mount agent that is listening on this port, and it is also exposing something. The process runs as root with high privileges, and I think you probably know where this is going, but just hang on. Additionally, we tried to look up the source code for this binary, but it turns out that it's a closed source binary. It's not open source like WA Linux agent or OMI. And we don't find any references as well. So we will have some debug information to understand the binary since it is not stripped. Now we crack open the binary using IDA to understand what is going on, and we come across a function that is called DSI start API service. Now this function exposes certain HTTP endpoints that can be accessed without any authentication for network adjacent resources. Now we start taking a look into the different URLs and what do they exactly do. So the first one executes a sync command on a file. The second one runs the mount operation, which basically checks and mounts the Azure file share on the compute instance. The third one helps view the OS image version of the compute instance. And the fourth one lets us view the list of services and their statuses. So examining the services endpoint, one could list the status of each service that is installed on a compute instance. So in this case, we have these many services and a lot more, but yeah, this is just a screenshot. We also see that one could see the logs of any service that is installed on the compute instance. So an attacker could basically list down the services installed, status of the service, the logs for the service, and this information could basically aid them in reconnaissance or performing lateral movement within such environments. So we had a simple information disclosure bug so far. But how bad could it be? For an example of what all could be exposed, here's a short little demo of what could a network adjacent attacker really see. While exploring the installed services on the compute instance, we see that Jupyter is installed as a service on the compute instance. Now, this is across all compute instances using Azure Machine Learning. And for each service installed, remember, we can view the logs since we are network adjacent and there is no authentication required to access the logs as well. Turns out, some commands are being viewed that were executed using the Jupyter terminal. And folks, this is where I went, okay, what did just happen? We saw some commands being logged in the Jupyter service. Instead of Jupyter, there could have been any other installed service. So basically, if there's an attacker that is on a virtual machine, which is a part of a virtual network, and on the same VNet, we have a compute instance. On the compute instance, we have DSI mount agent. That's the agent that is running. And this agent can fetch systemd logs for any service. And it exposes on all interfaces on this port, that is 46802. And there is a user that is using Jupyter to access the compute instance. And let's say if they run some command as sudo, and the attacker sends a request to view the Jupyter logs, this will actually give the command that was executed as sudo by the user on a compute instance. So basically, do you remember the mount command that was being logged in the first episode? Yes. So that was being run as sudo. So if a data scientist wants to mount a file share on their compute instance by themselves, by specifying the password within the command line, they have to run it as sudo anyway, and it will get logged, and that's like a silent risk anyway. So here's a quick demo of hacking the data scientist, which we called MLC. So on the top, we have the compute instance where the data scientist is running some command as sudo. And on the bottom, we have the attacker that is fetching the logs from the compute instance. So now we have the command line which contains the storage account password as well. And that will also get logged and that will be visible to the attacker. So we reported this vulnerability to Microsoft and they fixed it. We termed this bug as MLC, as a network adjacent attacker could possibly see the actions performed by a data scientist on their compute instance without needing any authentication. This was a very funny information disclosure bug. However, now the service, after the fix, the service does not expose the port on all interfaces and can only be reached over the Nginx proxy, which listens on port 44224. Some takeaways. At times, secret agents may lead to secret bugs and hence an expanded invisible attack surface. Also a silent threat. Vulnerabilities still exist in cloud agents. There is a need for focused threat modeling on various features that are given to an agent to perform. Because the attack surface that is introduced when you add some feature, where in this case, there was like sensitive information that was being leaked, that may be an issue. Practicing zero trust is definitely hard, but it's very crucial for cloud security. So the essence of zero trust is basically don't assume that just because something is already there in your environment, it should have access to other resources in your environment. Additionally, simulating attacks in secure configurations where, let's say, the VNet thing is something that Microsoft recommends as well. So they may uncover vulnerabilities in the service itself. And although this was an edge case, but this could be a silent threat lurking in your environment. Okay, so this is the bit about responsible disclosure. We found a way to achieve stealthy persistence in AML service, which allows for fetching of credentials from non-Azure environments. We reported this finding to MSRC via ZDI in April. But as a part of the disclosure process, we expect vulnerabilities to be fixed and acted upon time. Now, we requested a status check with MSRC as we found that the issue could be reproducible. And Microsoft responded back saying that they will be fixing the issue by end of August. As a responsible researcher, I believe it is not a good idea and would not be appropriate to disclose the details of this unresolved issue at the conference, as it could put users in a potential risk. Now, we move on to the funhouse of experiments, because it was a roller coaster ride finding these bugs and reporting it to Microsoft and getting them fixed as well. Here's what else we tried and we learned along the way. Failing is hard. We all go through it and it's a part of our lives. But we need to learn from our failures time and again. Here are some of the things that we tried over a course of 3 months and some of the things that we could not achieve. So we could not achieve cross-tenant scenarios. We could not also achieve dependency confusion in NPM packages. We could not find misconfigurations in the Jupyter implementation, apart from the one about the GWT token being logged in the access logs. So we now describe the container escape scenario that we had in Azure ML jobs to shed some light on what and how our approach actually looked like. So basically, a job can be thought of as a command to execute in a specific environment. And you can have training jobs, and you can, and using AML Studio and AML itself, you can track the metrics, the generated logs, the outputs, and you can gauge the performance of how your scripts are performing, how your training is happening, and all that stuff. So the environment in this case is specified as a Docker image, using which you can bundle all your dependencies, tools, and libraries that you need to run the job. And you can have 2 types of environments: curated environment. So basically these are publicly available Docker images specific to your requirement, and custom. So that means something that you can create from scratch. Okay. So you can create a training job and you can specify the compute type on which the job will run on. Okay. So basically you're running a bunch of commands on some sort of compute type. That's the gist of it. And it was still in preview mode when we were taking a look at it. So since these automatic computes, they had that mention that these are Microsoft managed. And you can specify the environment. So remember the Docker image thing, right? So you could create a custom environment with some basic tools installed like curl, wget, ssh, and all of these things. So we had a couple of questions. Where does the job run in and on what? We wanted to verify that bit. Could I escalate from the container onto the host? Is the underlying host being shared across other users or tenants? And are there any nearby hosts to poke around? So these were some of the questions that we had when we were using this service. So to figure that out, we create a malicious job, which basically fetches us a reverse shell. So we fetch the IP address by calling the webhook, and we modify our firewall rules to let the traffic in, followed by we download a Meterpreter implant on the autocompute container itself, and we execute the implant to get a reverse shell on my box. Okay, so since we are in a container, we don't see much happening, and there are just 5 or 6 processes that are running. In this case, it's just 4. So we try to perform a container to host escape using a mix of something that we have been observing on our honeypots, with threat actors doing all of that fancy stuff, and a little tweaking based on a famous open source tool called Docker Escape tool by Percussive Elbow. So basically, we were able to get onto the host and we were able to find a lot of our answers. And I was able to escalate from the container to the host, since the containers that are created in the AML jobs, they are privileged. So it's very trivial to escalate onto the host. And is the underlying host shared? So no, these hosts are not shared. So that's a good thing. And are there nearby hosts to poke around? So we ran some nmap scan within the subnet itself, and we scored the hosts of the jobs that we just created. So it was like a pool of VMs on which only our jobs were running. That's it. But we had one more question. Could the hosts be reused? So we wanted to verify that, and we wanted to look into creating a malicious job, which basically creates a file on the underlying host. We delete this job from the workspace, and we create a new job in the same workspace. The expectation is to see that the file is removed. That means the new job is running on a new VM. Okay, basically the new environment is on a new VM. But the observation at times was that the file existed. So that means the new job was running on the older VM that was already infected. We reported this issue to Microsoft, and they shared their feedback and closed it as by design. So jobs in automatic computes are run on virtual machines or nodes in batch pools that are unique and isolated per workspace. And each batch pool runs in its own virtual network. Now, jobs can at times reuse the same batch pool if they are available. So this was a good attempt of understanding how the environment looks like, and this is where we learned a lot of things. We found some bugs, they got fixed. We tried a few angles to our research and learned along the way as well. But where do we go now? Where do we go now from here? All right. Set up your environment using VNets, private links, and private endpoints. Why is this important? The storage account access key getting logged, the JWT getting logged, the agent exposing sensitive information in VNet environments. Exposing information, yeah. So having your defenses in place can actually help you reduce and eliminate cloud vulnerabilities at times. Fixed vulnerabilities that we shed a light on ring a bell so as to why following secure deployment strategies definitely ensure a defense in depth, and how it is quite effective against the possible silent threats that we just saw. Microsoft, in fact, made it very easy to go secure by default by offering these network isolation options while creating an AML workspace in the Azure portal itself. So that's very cool. Additionally, some basic stuff, you need to monitor your cloud environments for changes. Some storage account keys getting rotated, or some public access is enabled, anonymous access is enabled, all of that stuff. To detect, you need to know what you need to log. You need to see them first. So you need to set up your logging using cloud native solutions or CSPM tools as well. You can leverage various frameworks that are specific to Azure or the cloud that you are working on. In this case, I mentioned Azure Threat Research Matrix, which contains the Azure AD related various tactics, techniques, and procedures as well. Trust but verify. This is the most happy code that every InfoSec professional loves. And you need to verify the integrity of Jupyter notebooks, the scripts that you are using, the data sets, the models, as there is a very different attack surface around these ML entities themselves. Examine managed services to uncover silent threats. So you need to this is for the researchers, this is for other people that are trying to look into cloud vulnerabilities. You need to examine these managed services since they are maintained by the cloud vendor. So if you find a bug there, that will be reproducible across all the customers. And definitely, you need to implement the principle of least privilege. You could use custom roles, or the RBAC can be reviewed time and again and all that stuff. So specifically for machine learning environments, one can use the Atlas framework. That is, think of this like a MITRE ATT&CK framework, but for machine learning environments and systems. So Atlas also enlists various case studies around simulations and real incidents that are focused on machine learning environments, which can at times aid in understanding the current threat landscape for cloud-based machine learning environments as well. So in this case, we have these two are my favorite case studies, the compromised PyTorch dependency chain and the Azure service disruption. Now on the closing part, acknowledgements. I really want to thank my family members, friends, the Black Hat audience for tuning in person, although being virtual, my teammates, David and Magno, for helping me out in times of doubt, ZDI for smooth communication of the bugs with Microsoft and triaging as well. And there are a few more bugs in the disclosure pipeline that we are excited about. So stay tuned. Black Hat soundbites. Okay, so combat silent threats by practicing defense in depth. Risk increases when features and bugs combine. Secret agents, secret bugs, increased attack surface 2023. Even in 2023. We need to secure our present first, and with that, thank you so much for your time. I hope you have a great day ahead, and I hope to see you soon next year in person. Thank you.